This is Portfolio 2. The format will be calculation question, then concept question, since many of the concept questions are based on the calculation question. This is IQE 5 calculation question. For Sunday movie night, I decided to wear a soda hat for fun and to drink Coke without using my hands. Coke flows from a candle 0.5-inch steel straw that is 0.55 meters long with 3 flat 90-degree smooth bends at 1 gallons per hour. The viscosity of Coke is 1.44 centipoise. The density is 970 kilograms per meter cube. Straw has a change of height of 0.3 meters. Find the friction loss and pressure drop. Our knowns are viscosity, volumetric flow rate, nominal size 0.5 inches. We look up in Schedule 40 and we find the diameter is 0.622 inches. Loss coefficient stable. We look up flange 90 degrees smooth bends and we see that's 0.3 times 3. Since we have 3 of them, we get 0.9. Properties, we have density of Coke, viscosity of Coke, and we assume incompressible steady state, adiabatic, no flow work, and constant gravity. So to solve, we need to solve for average velocity. That's volumetric flow rate over area. We convert to SI units and we get 5.36 times 10 to the power of negative 3 meters per second for the average velocity. We use that to calculate the Reynolds number and we get a 55.2 for Reynolds number. So it's definitely laminar. It's a lot less than 300. So we can use the friction factor equation of 16 over Reynolds number. We get a 0.290 for the friction factor. To find the friction loss, we need to combine the minor and major losses. So we plug all of those in as we have already found them, and we get a friction loss of 5.93 times 10 to the power of negative 3 meters squared per second squared. Now we use Bernoulli's equation, and our velocity terms cancel out since the diameter doesn't change and it's incompressible, so due to continuity it will be the same. And we know that the height is 0.3 meters. And we said that for 0.2. Solving for pressure drop, we get 2.86 kilopascals. Pretty small, but it makes sense. It's a straw, so it wouldn't be that long, so the pressure drop wouldn't be that big. If the steel straw from the soda hat was shorter and had a lot more 90-degree bends, how would the head loss change because of this? Well, usually the minor loss associated with bend is less than the major head loss, but because the steel straw is short, it will not have a significant major head loss. And because there are many bends, the minor loss associated with this will be much greater than the major head loss of a short steel straw. IQE 6 calculation question. I visited Lake Pueblo and went boating. The temperature of the water was 10 degrees Celsius during the boat ride. I was journaling my experience and accidentally dropped my sail pencil into the lake when we were above the deepest part of the lake, 135 feet. The pencil has a diameter of 8 millimeters and a length of 19 millimeters and can be assumed to be falling into the water horizontally. Find the terminal velocity of the pencil. Known the length and diameter, we divide them and we can see from the drag coefficient table we get a drag coefficient of 0.9. That's table 11.2. Properties is density of pencil, density of the water, and viscosity of the water, which we found from the saturation table using the temperature. We assume incompressible, constant gravity, adiabatic. We assume it reaches terminal velocity, and we assume that Reynolds number is equal to or greater than 10 to the power of 4, since we can only use the drag coefficient table if that's the Reynolds number. We need to find the terminal velocity. Solution, we do a momentum balance. We do the weight minus the buoyancy force minus the drag force is equals to change in mass over time. Change in mass over time becomes m dv over dt plus v dm over dt. We know that the mass is not changing, so we said that equals to 0. And then m becomes density multiplied by volume. And the volume that we have here is volume of a cylinder. And dv over dt, we know that's acceleration, and terminal velocity is the point where acceleration is equal to 0, so the entire right term will be equal to 0. For the left term, we can take out volume and gravity, so we'll have pi d squared over 4 L gravity times rho pencil minus rho fluid minus the drag force. So we can rearrange this to solve for the drag force, getting this equation. And now we know the equation for the drag coefficient, so we can just plug in what we found for the drag force into that equation. Rearranging this, we can see that pi d squared over 4 terms do cancel out, and for terminal velocity, we get 2 length gravity, rho pencil minus rho fluid over drag coefficient times rho fluid. So we take the square root of that, and we plug in all our numbers, and we see that our units do cancel out, and we get 1.71 meters per second for the terminal velocity. Now we need to make sure that our assumption that the Reynolds number is equal to or greater than 10 to the power of 4 was correct. We plug in what we got for terminal velocity into the Reynolds number equation, and we get a Reynolds number of 1.046 times 10 to the power of 4. Reynolds number is greater than or equal to 10 to the power of 4, so our assumption was correct, and we can indeed use the drag coefficient table. Concept question is, you purchased a burger from Wow Cafe and added some ketchup to your burger from the ketchup dispenser by pushing down on the pump. What kind of pump is this? And explain how it works. This is a net positive displacement pump. There's an inlet where the ketchup can come into some volume inside and a piston that moves up and can decrease or increase the volume. As it increases the volume, it will suck the ketchup in through the inlet. When it decreases the volume, it will push the ketchup out the outlet. Also, there are spring-loaded valves on either side that keep the ketchup from going out the inlet when the piston moves up and lets the ketchup only go out the outlet. It also keeps it from coming through the outlet when you move the ketchup piston down. It allows the ketchup from a low-pressure source to get pumped to a higher pressure receiver by decreasing the volume of the chamber. It mechanically forces it to move. IQE 7. Calculation question. When making a dish that requires rice, I usually strain it before boiling it. To strain the rice, I put the uncooked rice, which has a particle diameter of 3.47 millimeters, in a cylindrical strainer that has a diameter of 30 centimeters and a length of 15 centimeters. I then pour water in the strainer. The water leaves through the mesh sieve at the bottom. The rice is packed such that 70% of the volume of the strainer is taken up by the rice. So we know that the particle diameter of the rice, and we know that the diameter is of the strainer, and the length, and the void fraction, which is 0.3. Properties, we just have the density of water and the viscosity of water. We assume steady state, adiabatic, no flow rate, incompressible, constant gravity. We need to find the friction factor, superficial velocity, and Reynolds number. So we use Bernoulli's equation. Pressure terms cancel out because the strainer is open to atmosphere on both sides. Velocity cancel out due to continuity, incompressible, and no changing diameter. And Z2 will cancel out because we will set that equals to 0, and 1 would be the 0.15 meters. So to solve with friction loss, we get gravity multiplied by the height. We get 1.47 meters squared per second squared. Then we use the ergon equation. Putting in all our knowns for the ergon equation, we get this quadratic equation that we need to solve. Using the quadratic formula, we get a superficial velocity of 0.0201 meters per second. Now we use the terminal velocity to find the Reynolds number. We get a Reynolds number of 99.2. This is transitional flow, which is okay since ergon equation can be used for laminar, turbulent, or transitional. Concept question. If I were to steam the rice from the bottom of the strainer and increase the velocity of the steam, the rice will float. Explain why this happens and how would it affect pressure drop. As I increase the velocity of the steam, the rice grains will float and the rice will be fluidized and behave as a liquid. The fluid flowing up causes the drag force applied on the particle to counter the weight force, which causes it to float. Because the velocity is increasing, the pressure drop will increase at a lower rate. Because when the rice was packed, the water had to overcome a solid barrier, but since the rice was fluidized, it now behaves as a liquid, so the water has to overcome a liquid barrier, which is easier to overcome. This causes the pressure drop to increase at a lower rate. IQE 8 calculation question. Every winter break, I take a plane to Oman to visit my family. Combustion gases enter the converging diverging nozzle in the plane's engine at 5,500 kilopascal and 2,500 degrees Celsius with a negligible velocity and a Mach number of 2.5. Find the exiting temperature, pressure, and velocity. We assume that the combustion gases are CO2. Since they're mostly CO2, we assume ideal gas, 1D flow, constant Cp, isentropic, and steady state. Known as the stagnation temperature, pressure, and velocity, and we know that the Mach number is 2.5. Properties, we get that from table A1. The K value is 1.288, the Cp is 0.8434, and the R hat is 0.1889. We need to find the exiting velocity, pressure, and temperature. So we use the equations from table A1 and we plug in all of our knowns and we get an exiting temperature of 1,460, an exiting pressure of 312 kPa, and to solve for the exiting velocity, we need to calculate C. That is root KRT. So we plug in all of our numbers and we can see that we have to use a conversion factor of 1,000 to convert from kilojoules per kilogram to meters squared per second squared. So we get 596 meters per second, multiply that by the Mach number, and we get 1,490 meters per second for the exiting velocity. This is really large, but since it's a plane, it makes sense that the velocity would be big. Concept question: what advantage would be gained from the plane nozzle having a converging diverging nozzle instead of just a converging nozzle? If the plane had a converging diverging nozzle instead, the combustion gases would initially accelerate until the back pressure cannot be lowered any further, and the flow will choke with a Mach number not exceeding 1. Whereas in a converging diverging nozzle, the diverging portion of the nozzle will cause the flow to be supersonic and surpass 1. As the nozzle diverges, the area will increase, but the velocity will still increase since the density is decreasing at a much faster rate, so the continuity equation is satisfied. The supersonic flow allows for the convective outturns of mass and velocity to increase, and although the pressure is less than it would be in a converging nozzle, the convective outturns of mass and velocity are so much greater than pressure that it creates a large thrust forward, which will cause the plane to accelerate.